Chapter 12, Elementary Chemical Kinetics. Section 12.1, Elementary Reactions versus Reaction Mechanisms. Chemical kinetics is the study of the chemical reaction rates and the mechanisms of chemical reactions. A chemical reaction may proceed in one step, so-called elementary step, or multiple steps, which constitute a complex mechanism. For example, this reaction between hydrogen and fluorine in the gas phase is likely an elementary reaction. So this hydrogen may attack one of the two fluorine atoms and form a transition state with a partial bond between the hydrogen and the fluorine. And also, this fluorine-fluorine bond is partially broken, and therefore we have a transition state structure with two partial bonds. And this structure resembles something between the reactant and the product. In the product, you have a hydrogen-fluorine bond. In the reactant, you have fluorine-fluorine bond. And in the transition state structure, you have two partial bonds. Well, another similarly simple reaction, the combustion of methane in oxygen, is a complex chemical mechanism. It consists of multiple elementary steps. So this reaction, looks easy, but there's no way for this reaction to proceed in only one elementary step. It is not always easy to tell if a reaction is an elementary reaction or consists of multiple steps. But an elementary reaction often has the following characteristics, with some exceptions. Number one, no more than two bonds are broken in an elementary reaction. No more than two new bonds are formed in an elementary reaction. It is rare to have three or more bonds broken or three or more bonds formed in an elementary reaction, except for concerted reactions, such as the Diels order reaction. Number two, it's often straightforward to draw the transition state structure of an elementary reaction by replacing the breaking bonds with partial bonds and the forming bonds also with partial bonds. For example, in this transition state for this reaction between hydrogen and fluorine 2, the FF bond is partially broken in the transition state. The hydrogen-fluorine bond is partially formed in this transition state. Conversely, it's impossible to draw the transition state for a reaction like this, the combustion of methane. You can try it, but in this, if there were a transition state, you would have to have, for example, 4 partial bonds between the carbon and 4 hydrogen atoms. And you need to have some partial bonds over here. And in the end, you need to have partial bonds between carbon and oxygen, and also some partial bonds between oxygen and hydrogen. I don't think it's possible to draw any transition state structure for this reaction. Therefore, this reaction must be a complex mechanism. For Diels order reaction, although I think we will have to sometimes break 3 plus bonds and form 3 new bonds. For example, if you have 1,3-butadiene reacting with ethylene, and in the transition state you have 6 partial bonds. 3 are considered partially broken, 3 are partially formed, but it's also straightforward to draw the transition state structure for the Diels order reaction. So the Diels order reaction is a elementary step. Now let's examine the combustion of methane in oxygen in more detail. In this reaction, we need to break 4 carbon-hydrogen bonds. We need to completely break 2 oxygen-oxygen double bonds, and we need to form 2 new carbon-oxygen double bonds and 4 OH bonds in this 2 water molecules. So again, it's just impossible to draw a single transition state structure, with all those partial bonds, and therefore this reaction, the combustion of methane and oxygen, just cannot be an elementary reaction. We can look at the simplified mechanism of this reaction. It not only involves multiple steps, but also multiple stages. First stage is initiation. We can produce some radicals, such as methyl radical, hydrogen radical, oxygen radical. And in this initiation stage, a lot of energy is required to overcome the barrier, because right here we're breaking a carbon-hydrogen bond. Here we are breaking the oxygen double bond. There are some branching reactions. So over here, this hydrogen radical can attack oxygen 2 molecule to form 2 radicals, hydroxide and oxygen radical. There is also propagation stage. Over here I listed the 9 elementary reactions. For example, a hydrogen radical may attack a methane molecule and form a methyl radical NH2. The methyl radical may react with a oxygen atom to form this is formaldehyde plus a hydrogen radical, etc., etc. So there are many reactions, elementary reactions in this propagation category. Also, there's a termination stage, because in the end, after the combustion is complete, the radicals actually can undergo those recombination reactions. So these 2 radicals may form a bond, and then we have a molecule with all electrons being paired. And in this reaction, very likely energy will be released, and this energy has to be taken away by something else. Otherwise, this product is not going to be stable. So we use M to denote some medium molecules that can take away the energy from the recombination reactions between the radicals. M star denotes the energized medium molecules. So M absorbs some energy released from this recombination of radicals, and becomes M star. And in this chemical reaction mechanism, very likely the initiation stage is the rate limiting stage. So very likely these 2 reactions might be the rate limiting steps. And I think it's gonna take more energy to break a oxygen double bond. So very likely all this reactions starts with the carbon-hydrogen bond breaking. So approximately, I think the energy barrier is just the energy barrier of this reaction, or the bond energy between carbon and hydrogen. Well, that's why if you just mix methane and oxygen, nothing will happen. You do need to ignite the reaction mixture. That means to provide energy to break at least 1 carbon-hydrogen bond. Once you have these 2 radicals, well, you can initiate many other propagation reactions or branching reactions. We talked about the difference between elementary reactions versus reaction mechanisms, but a chemical reaction may proceed in 2 or more reaction pathways, and it is possible that one of the pathways is elementary reaction and the others are complex mechanisms. For example, let's look at this reaction. H2 plus F2. We can form 2 hydrogen fluoride, and it can involve different reaction pathways. So first, let's look at one complex mechanism that involves multiple elementary steps. Step 1, we can break a fluorine-fluorine bond to generate a fluorine radical. So this is considered initiation. And then propagation, fluorine can react with H2 to form hydrogen fluoride and H radical. H radical can react with fluorine 2 to form hydrogen fluoride and F radical. And then this F radical can react with H2 again. So we have this two propagation reactions going on. In the end, the hydrogen radical and the fluorine radical form a bond, and we get hydrogen fluoride. Energy is released, and the released energy must be absorbed by some medium molecules, and that's why we need this M over here, and this M is energized after absorbing the energy and become M star. M star means energized medium molecules. Sometimes we can just use argon gas as the medium. Sometimes we can use some other inert chemicals as the medium for this reaction. This is the complex mechanism for this reaction. We can also make another conjecture that H2 and F2 may react in a different pathway that involves only one single elementary step. In this step, we have a four-centered transition state structure. So over here, this is the structure. We have four partial bonds. Hydrogen-hydrogen bond is partially broken. So is the FF bond, and then we have two partially formed hydrogen-fluorine bonds in a transition state. How do we know which mechanism is the predominant mechanism? So which one is the predominant pathway? Well, we'll have to do some quantum mechanical calculations. We can compute the energy barrier for this mechanism versus the energy barrier for this elementary reaction. Alright, whichever has a lower barrier is going to be faster, or considered as the predominant pathway. And we consider this like parallel mechanism because it's possible for H2 and F2 reacting in this described by this mechanism. Also, it's possible for H2 and fluorine 2 reacting described by this transition state. So both pathways are possible, and when there are multiple pathways in parallel, that means they take place at the same time, then the fastest pathway is the predominant reaction pathway.